We're now going to look at power series. These are a extension of infinite geometric series. So let's look at the basics of a power series. First of all, we notice that a power series is like an infinite geometric series. And if we'll remember, an infinite geometric series was a series represented by this summation going from 0 to infinity of a sub 1 r to the nth. And that was the first term divided by 1 minus r. And r had to be between 1 or negative 1 to converge on this number. If, of course, r is greater than 1, it won't converge at all to any specific number. This is now going to be rewritten as a power series, n equals 0 to infinity. And notice now we're going to use a sub 0, x to the nth. Notice r becomes x, and this becomes a power series, and that's equal to a sub 0 divided by 1 minus x, as long as x is between 1 and negative 1. Note that in these power series, n is going to begin with 0. A sub 0 is the first term. And we're also going to say that x can be replaced by any function of x. And that will produce a wide range of applications. Let's look at how we would replace x in a power series. First, let's take a look at, and for the sake of simplicity, when I write this, that means from 0 to infinity. And we're going to take x plus 3. Notice that now instead of having x, I have x plus 3. So that would equal, if it's going to converge, on 1 over 1 minus, and now the x is x plus 3, which simplifies to 1 over negative 2 minus x. If we want to write it, it's 1 over negative 1. Well, we'll just leave it as this. Now, over what range is this going to converge? Notice that here we have added 3 inside parentheses. The normal range is from negative 1 to 1. But in this series, since we've added 3, that's a shift of negative 3. So we'll shift each of the endpoints negative 3, and that gives me that this will converge over the range. 1 minus 3 is negative 4, and 1 minus 3 is negative 2. So x will converge between negative 4 and negative 2. Here's another one. The sum of x minus 1 to the nth. This would be 1 over 1 minus x minus 1, which simplifies to 1 over negative x. Well, let's see. 1 minus 1 is 0, and negative x. This would be converging And now the shift is +1. So I take my regular interval, -1 to +1, and that's going to shift to +1. So it will converge over the range from 0 to 2. So that's plugging in where we have a horizontal shift, because we're substituting x plus a number or x minus a number for x. Now let's look at multiplying the sum of 2x to the nth will equal to 1 over 1 minus 2x. But what's the converging range? Or the converging domain, I guess, correctly. Notice that when we're multiplying inside, that's a horizontal shrink if it's more than 1, so that's shrinking it. And so that would be, we would use 1/2. So my normal interval is from -1 to 1, and now we're going to shrink it by multiplying by 1/2, timesing by 1/2, and that gives converging over the interval -1/2 and +1/2. Let's take a look at this interval, 1/5, or x over 5 to the nth. That will be 1 minus x over 5. I would prefer to get rid of fractions, so we'll multiply top and bottom of the fraction by 5, and that gives me 5 over 5 minus x. What's the converging domain? Since I'm dividing by 5, that's an expansion, so I have to multiply the domain by 5, and -1 times 5 is -5, and +1 times 5 would be +5. So there we have a power series, how you can substitute in place of x other expressions, what the final sum will look like when you do that, and how you can find the domain over which it converges using what we've learned about the shifting and stretching and shrinking of functions in previous lessons.